جواب میرسه زنگ میزنم احتمال زیاد به کار
We don't even know what the weight credit is. Great. It might be like no more. No more.
Alrighty, good afternoon. Glad to see you all back after the midterm. Also, we'll be grading it probably Wednesday evening, so you will hear back on the midterm on Friday. Okay, so I will you about project phase 1. So we'll try to get everything back by the end of next week. So let's see what else to talk about. We'll talk more about the midterm once it's been graded and so on and so forth, how things went. So we'll just get at that point in time. So a couple of things. Project phase 2 has been posted since Wednesday. So you had a chance to look at what to do there. So what I have here is this sign-up sheet. And it's important that you select one of the goals for your phase 2. So there's 3 options. You have to pick one. You cannot try all 3 of them. So first one is minimize delay. Doesn't matter how much it's going to cost you in terms of power. Just try to go for the fastest possible implementation. A couple of rules, however. You cannot raise the supply voltage higher than 1.2 volts. Obviously, you can say, well, I'm going to start running at 5 volts. 100 volts, it might run faster, but that's not an option. Thing will fail before that. So 1.2 volt max is really the concern or the constraint there. Number 2 is for approximately, so I looked at all the phase 1 reports and tried to look at the distribution. Actually, most reports, obviously, like you look at the delay that you came up with, a large fraction of you are within a very narrow distribution, which is good. That's what you hope. It's the same design. You would hope that people kind of come up with similar answers. And they do. With some outliers, there's always some people who maybe have something completely different in mind or whatever. So I take that mean value, and let's say I add 15% in timing to it, approximately. Actually, I gave you a little bit more. So it's on the project that I posted. I say, here's the delay you are allowed to have. Maximum delay, worst case. Right? Not when your average case is worst case delay. Minimize, so I give you extra timing budget. Can you now minimize the power? Okay. What can you do? For instance, obviously, lowering the supply voltage is one. But you might be more clever as well in terms of the structures you use, how you basically control switching activity, all those kind of things. Try to think about what consumes power and how can I go after it. Okay? And then the third option is, I wrote 2 times the same thing, so let me change that. Give you 50% more power budget. So again, I looked at the average power that you came out for the same pattern that we have used before. You have a power. I give you 15% more power. What can you now do to minimize delay? So it's kind of similar to your first question, which is minimize delay, but here you have a power budget concern. You cannot, for instance, use the maximum parallel complex adder structures or something like that you might think about. So you have to constrain yourself and say, how much can I do now in terms of delay optimization without busting my power budget? Okay? So those are 3 options. So I'll pass those around for those of you who are here today. It's important that you sign up, you and your partner, sign up for one of those. And I put a max on it. We'll see if it is, actually, I might need a couple more. We'll see how it goes. But for each option, I basically allow 9 groups. If you run out of those, well, we have to add a couple more before. But obviously, first come, first serve in this game. I do first on, you get the first pick. So I'll pass it around. I think there's, given the people here, I think there's plenty of options. Those who are not here watching the lecture via webcast or delayed webcast, make sure you send me email as soon as possible, preferably before the end of the weekend. Otherwise, I'm going to do automatic assignment. I say, okay, what's left over? And I'll pick the groups who haven't signed up yet and randomly assign them to any one of those goals. So for those of you who are not here, send me email. That's the message. For those of you who are here, this is your opportunity to get your first pick. So I'll pass this around. And you can start working on this while the lecture is going on. And I'll, okay. So that's important. That's the first thing you have to do. You have about a week and a half extra, so it's no, a little bit more than that. It's due the 24th, which is a Wednesday. 23rd, is that a Wednesday? Yeah, I just worked from my memory here. 23rd, so you have time till then. Again, this is what I look for here is creativity. Think about how you can take this structure and make it better. So don't spend huge amount of times running through optimization through simulation. Think first very carefully about what are the structures I can play around with, how do I model them, how can I come up with a methodology to come up with a good answer. Because that's what I'm going to look for in the report. It's kind of what you say, well, you know, I thought about this problem and I think this is the opportunity that I have, and that's how I basically went in implementing it. So phase 3 then, the last 2 weeks, we're going to check if what you've basically been assuming was correct. So you're going to have to do the design in full, work it out completely, get the details down, and so on and so forth. That's the last 2 weeks to check if it really pans out or how close you really are to what you can come up in this particular phase. So this is high-level thinking. Okay, this is your opportunity to do your real design. So far what we've done is repeating what people have done before. Now you have to come up with your own interesting solution. And I think I reward, sometimes people completely think up with content. That's okay, if they're innovative, I'm always kind of open to, well, say, well, at least it was creative. And it didn't pan out, but it was creative. Sometimes those things are useful as well. Okay? So that's the project. What else? As I mentioned, we basically next Friday will return phase 1, midterm 2. We'll talk a bit about that. I'm going to go to some of the phase 1 issues. And then there's one extra thing. There's a homework running right now, which is going to be due next week, Friday. There's no homework due this week. And then we have still one lab to go. Next week is week 12. Time is ticking. It means that week 12, we have 4 weeks left in the semester. Amazing how fast things go. We're going to have the hardware lab in week 13, okay, which is not next week, the week after, and then we're done with labs. Okay? Any questions? Yes? You're signing up for something. You know, that's, you know, you can you imagine that you would work in a company and you would say, oh, yeah, well, I'm going to make a really fast design. And then you figure out, well, I do my whole design, and then it wasn't really fast. Let me change my goals and see if my boss agrees with them, right? So now you pick something and you stick to it. Okay, so think very carefully before you sign up. Okay, good. So another thing I decided to do is that, as you remember, last lecture I started talking about sequential logic and the idea to go sequential logic. I changed my mind a little bit, and there's a good reason for this. Actually, for those of you who, if you have looked at the project, what is the project really all about? It's basically a chain of adders connected together in a very intricate way. Turns out there's another logic structure which is very similar. Actually, it does almost the same thing. It's a multiplier. A multiplier is a chain of adders stacked on top of each other, connected in a weird way. So I thought it would be a good idea to talk a little bit about multipliers today and what people do to optimize multipliers, because I think it's going to be very relevant to what you're going to see happening in the project. So that's why I thought it would be useful to kind of move multipliers a little bit forward and then discuss, get back to sequential afterwards. Okay, so let's do that. So remember what we were doing with the project and the FIR filter. We have a number of adders and we have shifts. And the shifts, the amount of shifts you're going to be doing is going to be determined by the coefficients. Well, think about what a multiplier does. How would you do multiplication in hardware? Well, actually, the interesting part is you do it exactly the way you do it by hand. If you do multiplication by hand, what you do is you take your multiplier and you start taking digit by digit. You multiply and you get a partial product. I take the second digit, I multiply partial product, and I shift the partial product over a certain amount. And I keep on doing that till I'm basically gone to all the digits of my multiplier, and then I add them all together. That's where you do multiplication. Okay? So in hardware, we do exactly the same thing. If I look at a chip, and most chips these days, if you look at any microprocessor, like an, that has a floating point unit, you will have a multiplier in there. Typically today 32 by 32 bits, which would give you a 64 or maybe a little bit more, even 66-bit results. Okay? So exactly the same thing in hardware, but now in terms of, instead of using digits, we use bits. Okay? So it makes life a lot easier. So suppose I have to multiply this number here, 101010, by a number which is 1011. So what I do? Well, I start taking the first bit and said, let's multiply my multiplicand by this first bit. Now multiplying with a bit is very easy. When it's a 1, you just take the value. When it's a 0, it is 0. Okay? So if you think about from a logic functionality, what does that mean? It's an AND operation. I take the multiplicand and I AND it with that particular bit. When the bit is 1, bingo, a 1 becomes a 1, a 0 becomes a 0. When it's 0, you AND something with a 0, everything is 0. So you take basically your multiplicand and you AND it with the first number. That's this value. Okay? Take my second bit. It's again a 1, same value, but now since this is a to the power 2, I shift it over one position. Then I AND it with 0, you get 0, and then again I get 1, you get this. So what I end up is basically 4 partial products. And then to get your final results, I have to add them together. So here in the first bit position there's only 1, and then you can see you keep adding them. And obviously you will have carryovers and all those kind of things when it's happening. So there's an n bit addition. Okay? So this is what we're doing. You binary multiplication kind of written down in a binary fashion. So there's not much new in here. I already explained that. Here's my first solution to it. Actually, this solution is not very different than what you've done in the project so far. I say, okay, I take my first value, multiplicand in this case is x0 till x3. I take my first bit, y0, I AND it. So I just have a set of AND gates. I get my first partial product right here. I take the second bit, y1, I AND x with y1. Again, I have my second partial product. So I have 2 partial products. What do now? I add them together. Okay? I add a adder. Half adder, full adder. By the way, half adder, some of you might not be familiar with a half adder. Between a full adder. Full adder is something that takes in 3 bits A, B, and a carry. So, and basically creates a sum and a carry out. A half adder is when I have only 2 bits. Now first, when the carry is 0, I can simplify part of the logic. So a half adder is something that takes in A and B and produce S and C out. Okay? It simplifies the hardware a little bit. You can see I use half adders here at every time at bit 0. And actually sometimes when I have to add only certain bits, I can get away with half adders as well. But anyhow, so I take a full adder and I get a partial. I take the 2 first partial products and I add them together. Then I take this next bit, y2, I AND it, again, shift it, and add it. So what you do is shift, add, and then you're finally done. You get your results. And as you can see, I have here 4 bits in, and 4 bits, x0, so x0 till x3. The output of a multiplier, by the way, is going to be longer. I multiply 2 4-bit numbers together. You actually can get an 8-bit result. That's why multipliers always, let's say, a 16-bit multiplier will take in 2 60-bit numbers and produce a 32-bit result. Okay? So you can see that I can tap off the different bits. This is Z0, Z1, Z2, Z3, Z4, Z5, Z0, Z6, Z7. So I have 8 bits out of this particular structure. 4 bits in, 8 bits out. Okay? So that's cool. And I think that's the way you should have done phase 1 of your project. The only difference is now that the shift amount will be different, depending upon the coefficients I'm playing around with. Okay? But that's the most straightforward implementation of this particular logic structure. Now, this is also a quite bad implementation. Okay? This is not a really good logical structure. And I'll explain you why nobody will ever implement a multiplier this way. Remember, you want to make something fast. Okay? What's the rule of thumb when you want to make... Yes? Oh, okay, sorry. What's the rule of thumb when you do want to make something fast? How would you optimize a circuit for speed? Well, I said, gee, I'm going to try to find the critical path. I'm going to look at the longest path, and then I'm going to start working on it. For instance, one thing I could do is take all those adders that I have here. So, well, this is a ripple adder, like here. That's a ripple adder. Maybe I should use a look-ahead structure here. Look-ahead structure are faster, right? But then the question asks you, is this really going to help for your critical path? And the answer is maybe, maybe not. So let's figure out what the critical path is. So what do you think is the longest path through this logic structure? Any idea of how it would run? Totally unclear? You have done the project. You should kind of figure it out approximately. Yes? This one here, Z3, you can, this is a number of paths, right? This is one, for instance, one path. But why do you think this is shorter than, for instance, going like this? Or something that goes like this? They're approximately all the same, right? So that's the problem with this guy. Now I say I want to make it faster. How would I make it faster? Everything is critical. So there's so many different paths to this logic. It's very hard to do some optimization on it. So that's really the challenge of this array multiplier, is that you have a long critical path, which is approximately equal like this. You can play around with it, where m is the number of multiplicand bits, n is the number of multiplier bits. But it's a set of t carries and a number of t sums and some and things. There's one thing already that I start seeing that is different than what I would do. My first thing for an optimization would be is maybe I should change my adder. The full adder bit. Remember what we did when we optimized the full adder for a pure ripple addition? What was the most important concern? Is how fast I can get the carry in to the carry out. Right? Sum didn't matter that much. Right? Because you go to n carries and you only go one time to the sum and your critical path. Now you see that if you look at this equation, you see that t sum is getting more and more important. Right? So an adder which really has a very short carry delay and a long sum might not be the most optimal structure here. Actually making something which is more symmetrical, has maybe similar delay for the sum and the carry might be a useful thing to have. That's a circuit optimization. I can rechange or can change my full adder to make it better fit to this particular type of logic style. So that's option one. Obviously something you should consider when you start designing multipliers like this. But still, it still doesn't change my picture of my critical path. My critical paths, even if I do so, I'm going to change the balance a little bit between the different components in my equation here. So let's see if I can do something else. Could I restructure this way that I get a this block here, so that I get a very clear definition of my critical path? And then I can say, okay, now I'm going to tackle that critical path and make it faster. Okay? Well, there's something interesting to observe, right? What I'm trying to do here, you look at this bit, say this bit in this column. What I really do is I take two inputs. These are, remember, every one of those inputs is a multiplicand with an AND function, okay? And I add a third one. So I actually add 3 bits together here. Now you can imagine that the sum of those things, well, actually there's also a carry in coming in. So I have a carry in, 2 inputs. So there's 4 inputs to this network. So you sum and you get 2 carry outs. you can imagine that the sum value is independent of how I exactly combine them together. There's nobody says that I have to take this carry and add it here. Maybe I can feed the carry in here. Same result. Won't change anything. Right? So what I could do is start to reconnect the different connections in this and change the way I've combined different results together. So this is what I already mentioned. Symmetrical adder, I didn't know it, I had right after here. But here's an example, for instance, of an adder that has a fully symmetrical delay between A and B and C and the sum and the carry out. What I do here is I get A, I create a bar, I have an XOR gate here to create my propagate signal, and then once I have the carry in and the propagate signal, I just can combine this into sum and carry generation. You can see this is extremely symmetrical. You see the delay to the sum is exactly the same as the delay to the carry in this particular logic structure. As I already mentioned, something I would like to pursue. But let's get back to my restructuring. So suppose now what I do, remember what we did initially is take the carries of those guys and always feed them to the bit at the same row. Now if I now would just move the carry to the row below that, as I said, it doesn't change the result. The results coming out of there are going to be identical. So we just break every connection and we do this, we do that, we do that. We do this for every adder, and so on and so forth. So what I do is I kind of take this whole set of carries, this carry results, carry 0, carry 1, carry 2, and I move them to the next row below that. And I do this for every one of those. So I kind of shift that whole, I kind of skew the whole connectivity matrix of my adder. Now what's happening now? You see at the bottom, I'm not really done yet. Right? In the previous adder, multiplier, I have 3 rows of things and bingo, I have the results. But now by shifting those adders, this carries out, I still have here in the end, after 3 rows, I end up with a bunch of sum signals and a bunch of carry signals that I still have left over. Because from this one here, instead of going straight, I actually move this to the next row. So I need an extra row of full adders. Okay, let's do that. So we add those full adders and we add another adder at the bottom. Okay, so you say that's kind of dumb. Basically, instead of 12 adder cells, I now need 16. But look what has happened with my critical path. What I did is I broke all horizontal connections. There's no horizontal connection between your full adders anymore. There's only diagonal connections and straight down connections. Now if I want to find out what the critical path of this thing is, very clear. It's going to go like this. It's going diagonally down and then go to the last adder at the bottom. So that's nice because now I have one single critical path left over. And what I can do here at the bottom is to say, hey, there's a full adder here. One single full adder. It takes, like normal, a bunch of bits together. But we know how we can basically speed up a full adder. Actually, we know things like carry select, for instance. Or if I want to, actually, I can do carry look ahead. For this last adder, make this as fast as I want to. So what you get, your delay of your multiplier is now going to be n minus 1 times this t carry delay, and then the delay of this vector merging adder, and you're done. So my whole equation has become a lot simpler, and as I can make this merging adder as fast as I can shrink the delay of my multiplier quite nicely. Now, one interesting thing to observe is that if you look at this row, goes to 3, this goes to 3 delays, this goes to 3 delays, this goes to 3 delays, but here, these two already have 4 delays between them. Right? So you go 1, 2, 3, and then you go into this. This thing goes to 1, 2, 3, 4 stages. This goes to 3. You already see that we get this imbalance between the arrival times. Like here I go, if I look at this adder, this thing goes to 3 stages, but this goes to 1, 2, 3, 4, 5, 6. Doesn't that remind you of something about? That's the way we thought about the carry select adder. Actually, it turns out by just using a carrier select at the bottom here and very carefully setting up the blocks and so on and so forth, I can exploit that delay, difference of delay between the different arrival times, and actually get optimal results. So people are rarely going to use a look ahead adder here. Actually, a carrier select adder gets you darn close to the optimum you can get. So that's why most vector merging adders are going to be carrier select. Okay? So this is an example of an optimization you can do. This is called, by the way, this is called a carry save multiplier. And the reason for that is quite obvious. We have a number, we add two numbers together, you get a carry vector, and typically you would combine the carrier right away with the result, and you would get one result. No, we said we're not going to add them right away. We're going to save the carry vector and add them in the next row. So instead of basically combining the carriers right away, we save them here. That's all those red connections. We save them for the next row to perform. This thing is directly applicable to your FIR filter, this concept. Okay? It's one of the examples of things you could do. If you think about it, carry save arithmetic is something that works very nicely in add shift array type structures. So that's an opportunity, just a hint of something you might consider. There's other things you can do. Actually, I'm not going to tell everything. There's some other tricks out there that can make things quite nicely for you if you play them around. Okay? Now you might say this is kind of weird structure, right? If I would implement it this way, I would get on my hardware a block that looks like a trapezoidal. Now we don't like trapezoidals or triangles on a chip because it's very hard to fit them together. Square blocks are a lot easier to fit together than triangles or circles or trapezoidals. So any designer that comes up with a block like this is going to be frowned on. So what you typically can do is kind of modify a little bit. I would like to turn it into a square block, and actually it's not that hard to do. What I can do with all those full adders here, I can shift them one position to the right, and through the connections, I just make sure that I have the right connection between them. So rather than a trapezoidal, we can implement it like this, right? This is my first adder. My result comes in, and instead of feeding it to the next block, we basically have these diagonal connections now kind of shifted this way. And I can do this for all rows, and you can see that this multiplier now becomes a perfect square, which is very nice. The only problem is that the output comes out in two edges. The input X comes on the top here, Y goes on the left side, and the output is kind of wrapped around. So you're going to have to wire it out a little bit. That might create some extra wiring. But the block itself is nice and square. Okay? So that's one thing you could do. Yes? In this structure, you're going to increase a little bit of power dissipation because you have an extra adder. Right? You have an extra adder at the bottom. But be careful. It also, remember, think like balancing paths in logic. If you have a lot of critical paths or a lot of different paths with different lengths, you also create glitching. By doing some path balancing as we did here, we might eliminate some of the glitching that exists in the hardware. Right? So that's an important thing. But yes, power is going to increase a little bit. Thank you. Everybody signed up? Anybody want to change their mind? Good. All right. Cool. We're done. Yeah. But you have to be careful because there's a couple factors playing around. And multipliers, by the way, are very susceptible to glitching because you have these long critical paths with different lengths coming together, or long paths. You might see bits making up their mind and flipping back and forth a number of times. And I've seen multipliers where glitching was 30 to 40% of the power dissipation. Okay. So yeah, you add some extra hardware. Power goes up, but at the same time, if I make my critical path faster, I might be able to run the thing at a lower voltage. And I save power that way. Suppose I have a fixed timing budget. Right? So why would I make it as fast as possible? One trick you can do is make it real fast, and then you reduce your supply voltage. You get your V squared savings, and you bring it back up to the speed you basically want to get, and this way you can save power too. So I believe that actually this structure is substantially better from a power potential perspective than the first one as well. Good. All right. Now, how else could I make this thing even better than that? Okay. This is cool. Carry save multipliers. Fairly simple way to implement it. Obviously, everybody's going to. I said I've never seen anybody implement a multiplier with a bunch of adders and stacked in a row. You typically use carry save. Okay. So what else can we do? A couple of other tricks. Number one, who has ever heard about a Booth multiplier? Okay. CS150 material. Mr. Booth. Mr. Booth basically did exactly what we have done in the project. Booth multipliers are a way, using Booth techniques is a way for us to reduce the number of rows in our multiplier. Wouldn't it be nice right now to have 4? Wouldn't it be nice if we only have 2 rows? Right? Would that be cool? It's obviously going to be faster. Now remember what we did in the project with our coefficients? We said, well, you know, I have something like this. What you realize is that ones are important because ones create a real addition, but zeros are basically adding a 0 to something. Sounds like it's a waste, right? And that's why in the project we say, okay, we're going to maximize the number of zeros, and then we don't implement an adder when you have a 0 because you don't need it. It's adding something with 0, adding 0 to something. I know how to do that. It's the same result. Now in the multiplier we cannot really do that, but the same concept still holds. If I could minimize the number of ones I would have, and remember the same techniques that we did before. This is 1 0 1. There's a minus 1 0. This is 1 0 0 0 0. Sorry, this is minus 1 1 1. Minus 1 0 1. Minus 1 0 1. Okay. So I've gone from this representation to this representation, and you see I reduced the number of ones quite substantially. That's what we did with our coefficients in the project. But obviously this can only be done once you know the coefficient. Right? If I have the coefficient advanced, I can do this iterative algorithm. Now you can see this is an iterative algorithm. I have to do it a couple of times. I start with the first bits on the left. I do my first transformation, but then I see I get another couple of ones next to each other. I do it again, till you basically end up at the end. And you don't have anywhere 2 ones together. Then it's when it's finished. Now, iteratively taking this, now, however, look at the case where the multiplier is not known. I don't know the value in advance. Obviously, I cannot do this offline. I have to do this online. I could implement this algorithm in hardware. Right? I could do that. Iteratively compute, I take my multiplier, and iteratively I'm going to transform it into something like this that minimizes the numbers of zeros and ones. And then I say, okay, I should be able to get rid of some of those adders. The ones that basically, you see, I never have 2 ones together here. Okay? So you cannot do that. But Mr. Booth came up with is an algorithm that's very close to this. It says, okay, it's not going to be optimal, but I guarantee that per group of 2 bits, I'm only going to have 1 bit or minus 1 bit. You're never going to have 2 1 bits next to each other. And that's something I can do dynamically. It's not going to be optimal. You might be able to get away with smaller number of ones. But per 2 bits, I can guarantee there's going to be only 1 bit in there, or minus 1. It doesn't matter which one. Okay? So what a Booth multiplier does is says, okay, I take a multiplier, and I'm going to take my multiplier coefficients here. I'm going to feed it to some logic. It's a lookup table. You take your values in there. Here's your y coming in. And I do, out of this comes a transformed value of y, which is going to say, you multiply now the number not by 1 or 0, like we had before, but it could be 0, 1, minus 1, 2, or minus 2. Okay? So I'm basically, and I'm going to have only half of the values coming out of there. Per 2 bits, I only have one of those things. So you multiply. Remember, if I have only 1 bit per 2 bits, it's going to be either multiplying by 0 when it's both zeros. It's going to be 0, 1 when you have 0, 1. It's 0 minus 1 is basically multiplying by minus 1. If you have 1 in the 2 position, you multiply by 2, or you multiply by minus 2. You never multiply by 3 or minus 3, because that would mean that I have 2 ones next to each other. Okay? So with this we can define with some little changes here. We say, well, okay, now I get these coefficients in. I'm going to take my input value and I'm going to shift it over 1 position or 2 positions. Because multiplied by 2 is just shifting over 2 positions. And this -1 or +1, that's easily implemented. It's a subtractor or an adder. We know how to do that. Little XOR thingy, and you change the carry. So what boot multiplication does is, okay, I transform y, and I eliminate half of my adders. So by adding some little logic structure on the side. I have to do this inversion thing, and I have to select between shifting over 2 positions or 1 position. But that's not hard to do. So that's quite substantial, because now you see that delay in this direction is going to be reduced by half. Okay? Very nice trick for multipliers. Obviously, in our case, you've already done it. You know the coefficients, you optimize it, and you minimize the number of shifts and adds. So that wouldn't apply. But for multipliers with unknown values as the multiplier, this plays very nicely. So again, never implement, if I see a multiplier that doesn't use boot, I say that's really stupid. Right? It's a simple trick, and it speeds it up quite nicely. So please do it. Okay? What else could I do? Well, remember what we did with adders? It's kind of interesting that if I have to combine n elements together, right? What we say with adders is that, yeah, you can add them all sequentially. But actually, very often you're going to be better off if I kind of say, gee, I have to add these n elements together. Doing it all sequentially is a bad idea. If I do it in tree format, I can take all those inputs and combine them in a tree format. I'm going to need less logic stages. If you do it sequentially, you need n times the thing. If you use a tree, it's log to n. So, and that's going to be the fastest possible thing you can do. So log to n structures are very attractive. And the question now is, can we do that also for multipliers? Well, let's look a little bit at the logic structure here. So suppose I take one column through this multiplier. I might already have done both. It doesn't matter. That's orthogonal. What you see is I take here y0, y1, y2, then I add y3, y4, y5, and a bunch of carries coming in, a bunch of carries coming out, and a sum coming out. So I have basically a column of things I connect together. So if I count this thing, this has this is 1, 2, 3, 4, 5, 6, 7 numbers I want to add together. Okay? And I use 4 adders. Now, one thing you know about an adder, what it does, it's a symmetrical thing that takes 3 inputs and creates 2 outputs. So how many full adders do I need to combine 7 numbers together? Is it 7? Well, you have some intermediate results and things like that. But how many full adders do I really need? Can I minimize that thing by restructuring it and go more like as much as possible after a tree structure? So for instance, instead of taking y0, y1, y2, and then add the carry and y3, now why not just take, first of all, I take y0, y1, y2, y3, y4, y5, and combine those together with 2 full adders. 6 inputs in, 2 outputs that I have to combine further. And I get some carries on the way too. So I take another full adder. I have some other carries left. I bring those in. Turns out I need 4 full adders to implement this thing. Same number of full adders as before, but you see that my logical depth has now been reduced to 3 instead of 4 that I had before. Actually, you can imagine that this thing is not going to reduce it to log to n, but reduce it to log 3/2 of n. Why 3/2? Well, every time you take an adder, it takes 3 inputs, produces 2 outputs. So it reduces the number of you have a number of things I want to combine together. So suppose I need 15. Well, you start basically by 5 adders. You get 10 outputs. And you go further and so on and so forth, and you keep combining this together. So it's logged through 3/2 of m is the number of stages I will have in this. Okay? So that's the basic idea. Take your multiplier and rewire it. Rethink how it doesn't matter how you do it internally. As long as the results at the outcome are exactly the same, you're fine. So using tree structure is a good idea. So a lot of people have figured this out. If you look at literature, you will find some names like Dada multipliers. Dada is spelled with 2 D's after Mr. Dada. And you have a Wallace tree multiplier after Wallace. So a number of people have come up with different manifestations of multipliers that combine things together. And as a result of that, create a reduced critical path. Again, this is something that can be done with any stack of adders. Okay? Again, hint, this is something you might want to consider for your FIR filter. I'm not sure it's going to pay off, but it's something you might want to consider. Okay? So let me show you a little bit how this could go across. So here's your set of partial products. You have your multiplier. I have 4 bits by 4 bits. Right? So what you get is first stage is 4 bits, then 4 bits partial product, another 4 bits partial product. So if you would do a carry save structure, or basically the first row you have only 1 bit. Not much to be done, no addition to be done. Second column has 2 bits that you combine. Third one has 3, then 4, then 3, then 2, then 1, and you're done. Right? You can see that, right? Just because of the shifting, you see that in the middle I have to combine more bits together than, let's say, in the beginning at the end. Okay, I can reroute this. It doesn't matter when I add this guy together. If I have 1 bit to add, I just can bring this thing to the top here. I can redraw this picture. So, okay, here I have 1 bit to add, here 2, here 3, here 4, 3, 2, 1. So it's a triangle. And this triangle has a depth of n. Okay? Now, triangles are not very good because it's clear there's going to be a critical path somewhere here. Okay? That's what the longest path is going to create. So what I would like to do is transform this triangle into something which is square and flat. That for every bit level approximately I'm going to have to go to the same number of stages. So I'm going to reorganize it a bit. So remember, a half adder has 2 inputs, 2 outputs, a full adder, 3 inputs, 2 outputs. But one of them is a carry that goes to the next one. Right, so if I basically use a full adder, I create 1 output bit, and then I create an extra bit to add in the next column. Right, you shift it over to the next side. So let's see what I can do here. And let me just clear this out for a second. So again, you have your triangle. So let me start to transform this. I'm going to say, let's look at this top of the triangle first. Top of the triangle, let's say I take a half adder here. Half adder takes 2 inputs and basically creates 1 output and a bit in the next row. Okay? So this is going to collapse. If I use a full adder here, or a half adder, I'm going to collapse this thing into 1 point, but create a point in the next one. Right? That's the carry bit that I have to add to the next column. Same thing here. If I now say, well, gee, now this becomes 4. I make this thing 3, but I make this thing 4. That's no good. So I'm going to use another half adder here to move a point to the next row. So I've transformed my system now to a dot here and an extra dot here, and I simplified this thing to 3. That's my first chain of additions. So I use 2 half adder bits to kind of flatten out my structure. So that's what I get now. Here I can, let's say, if I take a half adder here, I'm going to reduce this to 2, but create a bit in the next one. Here, if I take a full adder takes 3 bits in one and creates 1 bit in the next one. So this is going to create an extra bit, this is going to create an extra bit, this create an extra bit. So if you put this all together, you have now a structure which looks like this. So this is stage 1, this is stage 2. Now here we're done. This is almost like a ripple adder. Right? I have basically combined 1 bit and then 2 bits, 2 bits, 2 bits, 2 bits, 2 bits, 2 bits. Bingo, ripple adder, we're done. This is our final adder. So what I did is transform this thing gradually into something that became 2 bits addition at every stage. And you're done. So this is a transformation that you can play around with. Just look at the logic structure. How much do I have to combine, and how can I now gradually combine as many bits together as possible? This is just one way. I could use other ways of combining them together. I could use 3-bit adders right away and so on and so forth. But the idea was to go after the critical ones first the top ones, and then I end up with something which is already a lot flatter. And notice I have 4 guys that I want to address, so let's do that. And now I have, bingo, all of them are basically the same or done. Okay? So it's something you can do very methodologically. Work through it and figure things out. And what you end up is a structure like this. Stage 1, remember, 2 half adders. Stage 2 is 3 full adders and a half adder. That's exactly the same. And you find out the routing between them. And then finally you have your vector merging adder, which combines everything together. You're done. Okay? This is a transformation of this very complex adder structure. And I basically methodologically try to find a way to minimize the critical path. Okay? So as I said, this could be applicable. I'm not sure. It's just something to consider when you play around in the project. But this is a very common way of doing things. Most high-speed multipliers that I see in floating point units on your microprocessor are going to be probably boot encoded Wallace tree multipliers. That's the basis. And then people in different companies, they have to get a paper in ISSCC, so they basically what they do, they make a little modification and say, well, I'm going to make a little change to the thing here, and my multiplier is now better because of that and that and that. So they write a paper and get published. But basically the idea is always the same. There's some, as I said, there's some variance to it, but if you got this, you're darn close to figuring out how fast I can make a multiplier. Okay? So this is kind of the thought process that you have to use when you start playing with the project. There's a number of options you can work with. Obviously, what adder cell to use, right? By the way, you're not allowed to change the register file. The register is a given cell. You cannot change it. That's an important one. So the only thing you can mess around with is the adder. And mess around is maybe not the right word. At least optimize. Let's put it the other way. You optimize is the adders. So you can think about what's the topology of the adder I want to use. Right? What is the circuit structure? You can think about changing the logic style. You know, instead of using complementary CMOS, I might use pass transistors or dynamic logic, and so on and so forth. So dynamic logic would be a way, if you really go after speed, I definitely would consider dynamic logic. Okay. But on top of that, you have to play around with the topology. You can play around with the topology of all those adders connected together. But if you're really creative, you also can play around with the initial equations you had. Nobody says that you have an FIR filter, that you have to have register, 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 and then you add all those things together. You can do some little transformations on this that might make it a little bit different. I'm just giving hints here, or potential thought processes. So it seems like a fairly simple block, but there's a darn lot of stuff you can do with it. And that makes this thing so much fun, I think. So that's why I think I will see probably 30 different solutions, or at least close to that. Because they're all different. If I get 30 times the same answer, I would be very worried. For a good reason. Okay? Good. So that's kind of the idea of how people do arithmetic optimization. How they take arithmetic blocks and then they kind of really worry about the critical path and they start messing around with the structure and how you combine things together to come to the optimal results. But typically, you will see that the fastest thing is always going to have somewhere like a log2 type of behavior somewhere in there. Because that's been proven, not by theory, but practice, that log2n, if you have n components, you combine them together, you're always going to need somewhere log2n number of stages. It's very hard to get around that. Okay. So a summary of this is, if you look at the multipliers, the optimization constraints are different than the binary adder. And the binary adder, it was carry in to carry out. That's really what we worried about. And the sum stuff was kind of a little bit on the side. In the multiplier, because you have an array structure, the dependencies are different. And you have to look at both carry paths and sum paths. But the bottom line is how to, first of all, identify the critical path and then find ways to get around it. How can I reduce it? And sometimes concurrency or parallelism is a way to get around it. Okay? So, and then you can start playing your games of like logarithmic versus linear, data encoding, That's the boot multiplier. Pipelining, if you have the opportunity to change the latency, and by the way, you're not allowed to change the latency in the project. You're not allowed to inject some registers in between logic stages. I have to get the input out, input goes in, and the output has to be there the next clock cycle. You don't say, well, no, it's going to be 20 clock cycles later, something's going to pop up. No, that's not allowed. Okay? So that's something I'm taking away from you. Because that would make actually the whole thing quite easy. I could make this thing one adder bit deep, and it's very hard to beat that. If I put basically registers in between every stage and I just let everything out. So that's not allowed. Pipelining is out of the option in the project here. But this is interesting because this is said, when you start playing around multipliers, you see already a whole bunch of ideas coming up that are playing very heavily in system level optimization. And that's the kind of fun part, I think. Looking purely at transistor sizing is cool. It's a nice thing to do. But actually the bigger gains if you look at transistor sizing in connection to higher level optimizations. I think because that's where you're going to get the biggest gains. All right. Let me, before I go back to sequential, let me just show you how different logic blocks or arithmetic blocks might need very different types of pieces of hardware. And the constraints of the optimization might be very different. Let me look at another block which is very important in a data path. It's called the shifter. Now you know how to do shifts. We've done it. But shifts by a fixed number are easy. Right? It's just wiring the thing up and you're done. You don't need any logic. But if you remember most microprocessors, if you look at the assembly, they have something like rotate left, rotate right, shift left, shift right over a varying number of bits. So the question is, if I now have to implement a shifter, not a fixed shifter, but a shifter by a variable amount, how would you implement it? Okay, what are the optimization criteria? Well, okay, suppose I would like to implement, first of all, a shift by one position to the left and to the right. How would I do that? Well, actually, it turns out to be very easy. I take, let's say, here's my input word, A, and I have bit AI and AI minus 1. And here my output bits BI and BI minus 1. So if I don't want to shift, I just take this output and feed it right to the output. That's easy, right? If I want to shift right, means that I'm taking the whole word and shift it one position down. What I just do is I take bit AI and feed it to BI minus 1. So I get this path. And the previous bit does the same thing. Okay. Similarly, if I want to shift left, I shift all the bits one position upwards. I'm going to take AI minus 1 and get it to a BI. Okay. So if you think about it, what this really is, from a logic block perspective, is a multiplexer. I take a multiplexer and I choose between the bit at the same position, or the bit just above me, or the bit just below me. And then I have a set of control signals that come in here and say shift left, shift right. Or don't do anything, no operation. Okay? So a shifter is a multiplexer. It's a multiplexing function. It doesn't do any other operation. It doesn't do any arithmetic on top of things. Okay, so I can do that. Now, suppose now I want to shift over 1 bit, 2 bit, 3 bits, 4 bits, 7 bits, 100 bits, whatever. Now, one way to do that would be to create a multiplexer with a whole bunch of inputs. 1 bit, like here I have 3 inputs, but if I would add shift 2 and shift left and shift 2 bits right, instead of 3 bits, I get 5 bits at the multiplexer. And then I need 7 and 9 and so on and so forth. Now you can imagine that's going to explode. Right? In terms of complexity. You have a lot of wires going all the way through this thing. And this node will be very highly capacitive, will be fairly slow as well. So is there a way for us to do this a little bit more methodologically? Right? Can I do a structured approach to implementing this shifter? So here's one first approach. This is called the barrel shifter. Now I don't know why it doesn't make me think about a barrel. but that's the name they gave around it, because think about it, actually if this would be a rotate left or rotate right, you see that the bits kind of flip around and the whole thing could be cylindrical and becomes a barrel. One thought process, but not sure. But see here how we do this methodologically. You take your input bits, A, and you feed them in horizontally over wires. Okay, so this is my input bits. Now, next thing I'm going to do is say, well, now I have to be able to take those input bits and connect them in a programmable way to one of the, let's say this is going to be shifting 1 bit down, 2 bits down, or 3 bits down, or 0 bits down. That's really what I would like to do. In a very methodological way, I would like now to basically to connect every one of those bits to one of the bits below that. How I can do that is actually quite straightforward, like I've shown here. You take really an array of transistors. Okay, so the first thing I do is I take my output bits. Let me change colors a bit. Color, just in color, the green. So, is this green? Yes, this is green. This is my output bits. Unfortunately, both of them run in the same direction. What I would like to have is kind of a grid structure where I can say, I make it into arrays. I want to connect this bit to this bit. I just have to put a transistor there. So the way we resolve that is by, let me find some blue. Okay, blue. So what I'm going to do is take this bits and ignore the details for a second here. I'm going to turn it to a vertical wire. So I'm going to connect this one here, this one is connected here, this one connected here, let's say, and this one connected here. Sorry, this should be under red. So I create a vertical, I turn the input wires and make them vertical wires. So the output wires are horizontal wires, the input wires now become vertical. And then on every cross point I put a transistor. Right? Any one of those cross points of the green and the blue wires, I put transistors down. Okay? So I get a complete array that allows me to connect any input bit to any output bit. This allows me for an arbitrary scrambling of my bit structure. Because right now, see, I can take input bit 3 and I connect it to basically output bit B3, B2, B1, B0. I can choose basically depending on how I turn on those transistors here at the cross points. Okay? So I fill it in. But that would be messy, because now I have 4 by 4, I have 16 transistors, which I have to control. For each of them, I have to bring in a control signal to basically determine what I'm going to connect to what. For an arbitrarily scrambler, I would need 16 control signals. However, for a shifter, it's easier, because you do the same thing for every bit. So in this case, and let me just now add one more color. Yellow. Yeah, let's do yellow. See if that works. I might not be visible. So for instance, I want to shift bit 0. Shift 0 positions. What I just do is enable all those transistors on diagonal, because this connects A0 to, what I have here is A0 to B0. That's shift 0. Same thing, this is A1 to B1, BA2 to B2, A3 to B3. So I can actually meander that control signal through the whole structure, and I turn on the transistor that are diagonally connected. Okay? I want to shift 1 bit. Well, I'm going to enable those transistors. This shifts everything down by 1 position. Now, depending on if you want to do a rotate, remember the difference between rotate and shift? Rotation means that you take your LSB and you add it back at the MSB side. You make it cylindrical. If you do a normal shift, you fill in the sign bits on the top, or zeros. If it's a positive word, I bring in zeros. But if you have sign bits, so it's a little bit different in how you're going to break it up, but it's the same story. So this is bit 3 bits. This will basically go this way. 2 bits is this. 4 bits, bingo, is that. So I can just nicely route my control signals through this whole thing and create any type of shift structure that I really would like to. Okay? So the nice thing about this thing is very structured. It hasn't changed the perspective. What I really did is I implemented a multiplexer with n inputs but I found a very constructive way of putting them together. But still, you see, if I want to do a 16 by 16 shift, I'm going to basically creating 16 input multiplexers. Because if you look at it, this structure here on the top is a 4-input multiplexer. Right? You have 4 pass transistors in parallel with each other. Okay? So the other thing that's very important, and you probably will see it when I do a layout of this. This is the layout of the same thing. It's nice and beautiful. It's actually, this is a layout that I kind of like because it's so regular, repetitive. You can see that you have here, you have your output signals, are those wires. That's your outputs. Just like we drew. These are the inputs, but then we turn the inputs around. They go basically vertical. And these polysilicon strips are your control signals. You can kind of nicely zigzag them to the whole structure. And this is very dense. It's very hard to improve the density of this thing. Because if you notice, if I look at where the transistors are, one thing that's very apparent in this structure, let me just change the color again. Oops. In color red. If you look at where the transistors are, this is a transistor here. Oops. That's a little bit more than I hoped for. Let me use Felton. So this is a transistor here, right there. Ooh, I went back to yellow. Oh well. Beautiful software. Okay, this should be right. There we go. So you see the transistors are actually quite small. If you look at the whole area of this block, and you count how much of the area goes to transistors, you see that's actually only a minimal fraction. Most of this thing is dominated by wiring. The wiring in this direction, the wiring in the vertical direction, the control signals you have to wire through them, and so on and so forth. So if you have to optimize the area of this thing, it's not minimizing the number of transistors or the size of the transistors. I easily can make the transistor a little bit wider here if I want to make it faster without getting an area penalty that's really big. It is really the wiring that dominates it. So a very different perspective than, let's say, if you do a multiplier. If I do a multiplier design, it's your transistors that are going to dominate. Here it's wires that dominate. So very different logic structures are going to have different type of determinant factors. Okay? So this is my whole shift array, and obviously I need the buffers at the end here. These are your inverters that basically create the outputs. Okay. Now, this looks cool, but it has a problem. It still has that problem that I was mentioning. If you look at the delay of this guy, it's going to be linear in the number of bits. Why? You look at your multiplexer. What I basically do is create a multiplexer with n inputs, right? And the more shifts I'm going to do, or more shift positions, the larger the number of inputs to that multiplexer is going to become. This capacitance is going to increase quite substantially. Okay? So you get a linear dependency on the number of shift bits. Now we don't like linear things. Although they're kind of nice. Well, you should never be more than linear, that's for sure. But linear is we know we can do better. We know in everything we do in logic, we always can do log to n. Right? That's the rule. If it's not log to n, I think there must be something that is not optimal. So, question is, can I make this structure here into a logarithmic one? And the answer is absolutely yes. Okay. So what we did here now is the following thing. I said, okay, you have to shift by 1 bit, 2 bits, 3 bits, 4 bits. I'm going to do all of them, and then I'm going to select linearly using a multiplexer between the different choices. Right? What else could I do? Any idea of what another option would be? How could I turn this thing into something which is logarithmic? Any thoughts? Shift by 7 bits. How would you do shifting by 7 bits? So you can either have a wire that goes over 7 bits, or I can do something a little bit different. How about breaking it down? And if I shift over 7 bits, it's equal to shifting over 4 bits, over 2 bits, and over 1 bit. Right? If I add those 3 together, I add something that shifts over 7 bits. So I just take the binary representation of my value and I break it up. I have a 1 or 0 bit shifter, a 2 or 0 bit shifter, a 4 or 0. I just use the binary numbers, the log, or powers of 2. And then by combining them, I can do any type of shift value that I want to. I make it programmable. Like shifting over 5 means shifting over 4 and shifting over 1 position. Now think about it. If I have n bits in my shift position, let's say I want to do a shifter that goes all the way to 7. That's 3 bits, right? 3 bits would be 2 to the power third options that I have. But by using a shift over 4, a shift over 2, shift over 0, I only have 3 stages. Log to n again, like we did before, like we did for adders and multipliers. Same thing happens here. So this is an example. This is now a shifter that is logarithmic. Instead of basically combining all possibilities, now I create first of all a shifter that shifts over 0 or 1 position. It either feeds it straight forward or it takes the previous bit. Easy to do. Second one is a shift over 2 or shift over 0. Okay? You're not taking, now I'm going to take, let's say, bit A3. I'm going to kind of meander it through here and fit in here. And then you can go even more complex. You can do over 4 positions. You can see this thing comes in on the top here and goes all the way 4 bits away. Now you can see that subsequent stages are going to get more complex. It's 0 bits and 1 bit is easy. I just take the previous bit or the current bit. Shift over 2, I have to go 1 slice away already. 4 bits, you have to go 4 slices away. 8, you have to go. So you see the wiring here obviously is getting more and more complex. But overall, you see that I implement this whole thing with only 3 stages. So as a result, the load here is going to reduce. Now you might think that this is going to take more wiring than the other case, but actually it does not. Because of the fact that I have only logged 2 stages, even from a wiring perspective, when you do large values, this thing is going to win also in area. So this is kind of an implementation of it. It's this is your first shift stage, sitting right here. I think this has buffers at every stage. Yeah, these are the buffers. Shift stage number 0 or 1. This is 0 and 2, buffered. This is 0 and 4, buffered. You can see that the meandering of the wiring becomes a little bit more complex. This has almost no wiring. Here you can see this little zigzag wire appearing. Something that goes from here through the next bit to the bit over there. And then you can see this complex guy here that goes. Very cleverly designed though, by the way. If you look at this wiring, you see they have 4 wires, 4 pitches, metal pitches only, and I managed to squeeze all those wires on the same layer. This, by the way, is called the river route. River routing is kind of this very nice, you have a number of n bits and you have to route them through. You see these little wave structures appearing. That's why they call them rivers. You see this whole thing kind of zigzags back and forth like waves on a river. That's why they call it river routing. You know, people occasionally have to be imaginative. Okay, but you can see that you can make this thing very nice, very compact, and it turns out that the width of this thing is actually quite good. It's actually going to, from the time that K gets large, it's going to be better than a barrel shifter in terms of area because of this log-to type of nature. Okay? So again, what I wanted to emphasize with this thing, why I went to this shifter thing, is that you have to be very careful. Right? Depending on what you want to optimize, you're going to play with different type of function, different things you're going to look at. It's either going to be the number of wires, number of transistors, combination of the two, and so on and so forth. Right? For instance, look at we're going to show later some SRAM cells, for instance, memory cells. And we're going to show how people optimize those things. And it's a very careful balance between the number of contacts you have, number of wires you have to create, the number of transistors that you're going to have, size of transistors, and so on and so forth. That's the whole layout game that we're going to play. Anyhow. Good. So that's what I want to talk about. Yes.
So do we need to use the level restorer in this case, just like a PDL?
Yes. If I would implement it this way, I would definitely add level restorers. because obviously this NMOS pass transistor logic, the buffers have to be restoring, otherwise this thing is going to leak like a sieve. So yes, absolutely. But you can imagine that using transmission gates here would be a really bad idea. So using NMOS only means that in this whole array, I use only NMOS transistors here. Like here, that's only NMOS. If I would actually have to have PMOS device there as well, it would double the area for sure. So it's actually cheaper for me to add some level restoring functionality in the strings. The other thing that I can do is eliminate some of those buffers. There's no reason in the world that I have to have a buffer every stage. Actually, this design is way too conservative. Because remember, fan out optimization, I'm going to be just as fast, if not faster. Actually, I'm going to be faster if I have 3 pass transistors in a row than having pass transistor, buffer, pass transistor, buffer. 3 pass transistors in a row gives me about the max, the optimum type of ratio between buffers and basically switches. Like we see 3 to 4, depending, somewhere between the two. Remember, the magic number 4 is always coming back here. Okay, good. That basically is what I want to say about arithmetic. This was chapter 11. I could start in sequential logic, but I have only 5 minutes, so I'm just going to chat a little bit about other things that are fun in arithmetic. There's other logic functions that you might want to implement. Right? Log functions, things like sines, cosines. You might wonder how a calculator implements. You have your little HP calculator, whatever brand you have, TI, doesn't matter. You might wonder how they do these sine functions and cosine functions and tangents and all those kind of things. So there's a whole branch of logic design which is called arithmetic. There's a whole bunch of conference which is focused really on this particular topic, how to do fast arithmetic. And there's a number of ways of tackling this that might be interesting to be aware of. One thing you could do, one simple way to implement logic functions is to say, well, if they're very complex, trying to build an equation that's going to implement this might be complex, right? For instance, I can take a sine wave and I can do Taylor expansion. That would be one option. I'm going to Taylor expansion and I'm going to take maybe the first 7 factors and then I'm going to throw the other ones away. Would be one way, but it's not the optimal way. There's better ways of doing this thing. Another way is just saying, well, I'm going to store it. If I basically have, let's say, a sine wave, what I could do is store some of the basic values in a scaled format, and I put them in the table. I have somewhere a chunk of memory, and I stare myself, well, for this point, that's the value that should get out. For this point, you get this value. For this point, you get this value, and so on and so forth. So I just put the x value as the input here, and the y value comes out on the other side. That's called table lookup. Table lookup, TLU. It's you put it in a memory, and you apply the input on one side, and the output comes out on the other end. Now you can imagine that if you want to have precise arithmetic, that would be a problem, right? If I want to get 16 bits accuracy out of this thing, or 32-bit accuracy, you can see that the value of this table could be huge. It could be giant memory. So that in itself is not going to fly. What else can I do? Well, table lookup is a good idea, but what I can do is table lookup combined with some other things, like interpolation. There's some ways to get intermediate results. You can do linear interpolation. I could do quadratic interpolation. You take 3 points and you find out what the point is in between. So the combination of those two is very powerful. Very interesting way of doing arithmetic combinations. And then there's some other functions, the other approach that people take. One thing that's very popular is an approach which is called Cordic. And Cordic basically allows you to, it's a very beautiful algorithm that allows you to using only adds and shifts to do anything which is square roots, sines, cosines, tangents, and things like that. It's a pipeline data path, and the only thing you're going to do is adds and shifts. It's kind of a Taylor expansion. The accuracy basically is going to be better with the number of stages you have. The more stages of adds and shift you create, the more accurate you get. But this is a very popular algorithm, and that's what you're going to find in most of your hardwired implementations, that where you want to get those goniometric functions. Quadratic is what people do. And as I said, it's just stages of adds and shifts and pipeline registers in between them. Okay? So very popular, very interesting thing to be there. But I just want to mention that you should be aware there's a whole field out there where people try to figure out how to compute complex logic functions and do it fast. One last thing that I want to ask you is, for instance, there's another set of logic functions that you might want to consider as divides and square roots and things like that. Question is, you might want to think a little bit, how will you do a divide? And if I want to build a hardware divider, how would you do it? Divide by any number. Any idea how you would tackle it? Yeah, yeah, but be a little bit precise. Yeah, definitely don't be shift and adds. Know that. Yeah, thank you. But how do you get a reciprocal? That's 1 over x. That's still a divide. Mm-hmm. Yeah. Yep. You're basically very close to it. How do you do division by hand? If you still remember how to do that, right? Maybe people don't know anymore because now you have calculators doing it for you. But it's like a multiplier in a sense. What you do is you take the word and you subtract the divider, and you try it out. You first shift it at the MSB bit side, and then you say, okay, is it larger than 0 or smaller than 0, the result? If it's larger than 0, you say, that's fine. I basically picked the right number. You shift the value, and you subtract again. And if it's negative, you say, well, I shouldn't have done it. I'm going to retract what I did. So you do exactly the same as you do by division by hand. It's a reverse and basically a sequence of add, subtracts, or add, subtracts, and shifts, like we would do by hand. So if you remember doing division by hand, you should be able to do it by a computer as well. It's very similar to that. Now, optimizing the speed of that is a different ballgame. It's not easy because it's a sequential algorithm. You subtract, then the next one, then the next one, then the next one. Anyhow, that's really what I wanted to say about arithmetic. Next class, we're going to go back to sequential logic and talk about registers, timing, and all this kind of good stuff. Okay? See you next Wednesday.